High power LEDs are the LEDs with better light extraction, improved capability of operating at high currents, and more virtuous heat confication techniques and so on compared to low power LEDs. The following table shows the specification and characteristics of low, high, and ultra-high power LEDs. Thermal management is important in LEDs because significant part of electrical power convert to heat. Only 20 until 25% of the input power in the LED is transformed into light, and the remaining 80% until 75% produce heat. As the junction temperature rises, the internal quantum efficiency of the LEDs fall. By interdiffusion of materials, defects are created in the crystal structure. On the whole, the LED might either continue to operate with reduced efficiency over a shorter lifespan, or if the temperature rise is excessively large, it may be damaged completely. For most commercial LEDs, the junction temperature cannot exceed 120 degrees Celsius. Therefore, it is crucial to rapidly remove the heat and keep the junction temperature below a certain limit for the maintenance of performance. High temperature causes a short-term effect on electrical behavior and optical characteristics of LEDs. As the forward current flowing in an LED increases, its temperature increases and the forward voltage drops. As a consequence, the light output will decrease because the input power has abated, and the brightness of the LEDs and its efficiency decrease as the temperature rises. While long-term effect on high temperature cause white LED die, the non-uniformity of current flow leads to localized heating and resulting in hotspot where the temperature rises excessively. Ultimately, the device is burned. Second, high temperature for extended period of time cause the absorption wavelength of phosphorus change. Such degradation of phosphorus material by thermal exposure adversely affect the LED performance. Both thermal exposure and silicon of LED encapsulant turn yellowish with heat and time, whereby the color of the output light change causing a decrease in LED efficiency. And some packages become yellowish with time and heat, affecting the color of emitted light. An effect of thermocycling, the LED is subjected to the extreme limit of temperature day after day throughout the year, leading to expansion of LED parts during heating and their contraction on cooling, undoubtedly shorten the lifespan of the LED. Thermocycling weakens even the resistant component because it produces micro cracks and triggers adhesions and delamination issues. Plastic materials crack under thermal stress, solder joints become loose, and bond wires are broken, resulting in failure of LED and drive circuit components. There are three different types of heat transfer. First is conduction, which is an energy transfer from the high temperature region to low temperature region when a temperature gradient exists in the body. And then second is heat convection, which is heat transfer process caused by the mixing of hot and cool fluids because of the macroscopic motion of fluid, which gives rise to the relative displacement within parts of the fluids. And then the third one is thermal radiation, which is a process by which the surface of an object radiates its thermal energy in the form of electromagnetic wave. Therefore, heat can directly transfer in a vacuum without any medium by radiations. And the thermal resistance is a resistance of heat transfer that defined as R equals to delta T over Q, where delta T is a temperature difference of some critical component and Q is the heat flux of the component at steady stations. The design of LED packaging are divided in three categories. First is optical design, second is thermal management, and third is drive circuit and intelligent controls design. And here we will only focus on thermal management. And thermal management is divided in 4 different levels. Level 1 is LED chip, level 2 is a submount, and level 3 is carrier substrate, and level 4 is system level. In level 1, there are 3 common LED chip structures, which are horizontal, vertical, and flip chip that show in the diagram. The horizontal LED chip suffers from serious problems such as current clouding, high forward voltage, and poor heat dissipation due to the non-electrical conductivity and poor thermal conductivity of sapphire substrate. While the vertical LED have uniform current spreading, smaller thermal resistance, and higher light extraction efficiency. And last, the flip chip LED is more attractive candidate for LED packaging because it makes high conductivity and more reliable LED chip with high current spreading ability. While the 3 common kind of material used in LED chip are sapphire, silicon carbide, and silicon. Sapphire is the mainstream of LED chip manufactured due to cheaper price, even it has a low thermal conductive material. While silicon carbide is high conductive material that have better thermal expansion mismatch and lattice mismatch compared to sapphire, but it is expensive. Last, the silicon is cheap, good thermal and electrical conductivities, but it suffers from high lattice mismatch. In level 2, submount is a small wafer which usually attached underneath of LED chip to accelerate amount and rate of heat dissipation and compensate coefficient of thermal expansion mismatch between LED chip and carrier substrate. Thermal management of submount mainly focus on submount material, die attachment material, and electrical connection of LED chip. The most common use of submount materials are silicon and aluminum nitride. While the die-attached material can classify as organic and solder adhesive. Silver epoxy is most popular die bonding material in classical LED package. Highly thermal conductive gold-tin solder is most prevalent solder used in high-power LED packaging. Nevertheless, electrical connection always associated with heat generation. This amount in LED packaging is negligible. In level 3, substrate is a carrier for LED chip or model to protect them mechanically and prepare their electrical connections. The dissipated heat can be expected in larger surface when reached to substrate. Thermal management of LED package at substrate level has good potential to improve the thermal performance of whole LED packaging. In this section, potential of carrier substrate material, TIM, and manufacturing-based solution for improving the thermal conductivity of LED packaging are discussed by detail. There are 3 most prevalent kind of material are used in carrier substrate are board, ceramic, and silicon. While the studies show that 60% of thermal resistance of a system is in thermal interface material (TIMs), while the thickness of TIM should be strictly controlled to make low thermal resistance. Last, fabrication best methods are related to microfabrication process such as fabrication of thermal vase solution (TVS) and reflection cavity and LED chip models configurations. Last, system level. The main focus in level 4 is airside cooling of LED lights. The 8 commonly known methods of air cooling are natural convection heat sink, synthetic jet, piezoelectric fan, thermal glaze, liquid cooling, and heat pipe. Among thermal management of system level, while fans have acted as a dependable active cooling technology, synthetic jet has established themselves as a front runner for cooling LED lights due to their high reliability and low acoustic performance. While the following diagram show that the fan and heat sink, which black color show the fan and silver color show the heat sink. After all the discussion, We conclude that thermal management of LEDs has become an essential topic for us, and without an effective thermal dissipation solution, the lifetime of LEDs will be greatly reduced. And that's all from me. Thank you.